In a quality control test of parts manufactured at Dabco Corporation, an engineer sampled parts produced on the first, second, and third shifts. The research study was designed to determine if the population proportion of good parts was the same for all three shifts. You are given the sample data, and we are asked, using a 0.05 level of significance, to conduct a hypothesis test to determine if the population proportion of good parts is the same for the three shifts. So what I'm going to assume is that they are the same, that the percentage of good parts for shift 1 is equal to the percentage of good parts for shift 2 is equal to the percentage of good parts for shift 3. And I'm going to see if there's sufficient evidence to reject that and conclude that that statement is not true, that they are not all the same, or that there is a difference somewhere between those percentages. Now I'm going to go ahead and get the data and put it here in a table. So I've got the observed frequencies, and I've included the totals, total number of good parts, total number of defective parts, for a total of 900 in the sample, and a total taken of 300 from shift 1, 400 from shift 2, and 200 from shift 3, again totaling 900. Next thing I want to do, I put my formula there to calculate the expected frequencies to run a chi-squared test. Since there are more than two populations, I'm going to need a test statistic, and so I'm going to have to calculate that with the observed and expected frequencies. Now the first calculation there for shift 1, there were 285 good parts. That value is in the first row and the first column. So row 1 total would be 829. Column 1 total is 300, so I'd multiply those and divide by the sample size total of 900. And that will give me 276.333, or I'll just put 3 bar there, and I'll put that as my expected frequency, 276.3 bar. Now again, to try to make a little sense of why this calculation is true, there are 900 total parts in the sample. 300 of them came from shift 1, and 300 divided by 900 is 33.33%. And there were 829 good parts, so since shift 1 had 33.33% of the total sample, that's, if the null hypothesis is true, you would expect that that's the percentage they would share of the 829 good parts. So I would multiply by 829, and then I get my 276.3 bar. Okay, let's go on to the next one. Go to 368. That is in the first row, second column, so I want the row 1 total, 829, and it's in the second column, so I want the second column total, 400, divided by the total sample size of 900, and I get 368.44 as my expected frequency. And putting it in my table here, 368.44. And again, to make sense of that, the second shift had 400 out of the 900, which is 44.44 etc. percent, and they should, since they share that percentage of the total sample, should, if the null hypothesis is true, that percentage, they should share that percentage of the total number of good parts. So multiplying that by the 829 gives me the 368.44. Okay, let's go on to another one. The 176. And that is in the first row, third column. So 829 times 200 divided by the 900. And that gives me the 184.22 expected frequency for the third shift. And then, let's keep going here. Hope you're getting the pattern of this. It's almost like you can just remember what to do as opposed to trying to really remember too much of the formula. Okay, for the first shift number of defective parts, that's going to be in the second row, first column. So the second row total is 71, and I'm going to multiply that by 300 divided by 900. And I get 23.67. That's my expected frequency. And for 32, that is the second row, second column. So the second row total times the second column total divided by the sample total. And that's going to give me 31.56. And then one more. 24 is in the second row, third column. So the second row total times the third column total divided by the sample size. And I get 15.78. So I have all my expected frequencies. Now I need to calculate chi-squared, so I'm going to be using this formula, and that's telling me to find the difference between the observed frequencies and the corresponding expected frequencies, squaring those, dividing by the expected frequencies, and doing that across each row and column. So I'm going to start, I have basically 6 calculations to do here. So my first one is 285 subtract 276.3 bar squared over 276.3 bar plus, let's go on to the next one, 368 subtract 368.44 over 368.44, and then 176 subtract 184.22 over 184.22. Keep going here. I've got 15 subtract 23.67 squared over 23.67. plus 32 subtract 31.56 squared over 31.56 plus 24 subtract 15.78 squared over 15.78, and I get a total for chi-squared at 8.10. So this is my chi-squared value, 8.10. Now I'm going to move to the top of the screen here, over here to the right, and going ahead and running the test. So let's see. I'm going to use my chi-squared distribution and my alpha equal to 0.05 to look up my chi-squared critical value. So chi-squared sub alpha, or chi-squared sub 0.05, is equal to, now I'm going to go to the table, there are three categories, so 2 degrees of freedom, and 2 degrees of freedom with 0.05 in the upper tail, I get a critical value of 5.991. And I'm going to reject H sub 0 since my test statistic of 8.10 is greater than 5.991. And I will conclude that there is a difference in the percentage of good parts produced by the 3 ships. So I've actually been able to prove something here statistically, that I have statistical significant evidence to show that these percentages are not the same, that there is a difference. Now I could also run this test by using a p-value, and again we are at 2 degrees of freedom since there are 3 categories. We're on row number 2 in the table. My test statistic is 8.10, and that is, if you look at row number 2, cross row number 2, that is between 7.378 and 9.210. So my p-value must be between 0.01 and 0.025. Again, the largest it could be is 0.025, which is less than 0.05. We get the rejection. If I use Excel to calculate the p-value, then the p-value turns out to be, it is between 0.01 and 0.025. It's actually 0.0174, again greater than 0.05. So we were allowing a 5% risk basically in making a type 1 error. In other words, we didn't want any more than 5% chance that if we rejected the null, we'd be wrong. And the risk is less than that. So again, we would reject H sub 0. And whether you use the test statistic critical value approach in deciding on what side of the distribution that's on, and by the way, that 8.1 is over here to the right side. So in other words, I'm far enough away from what would be going on if the null hypothesis is true to go ahead and have confidence in rejecting it. Or using the p-value approach. They will both agree.